Hey guys, it's Stack Lessons, another practice run for you, 20 questions, covering RAG chunking architecture, endpoint sizing, and evaluation metrics, 10 seconds per question to lock in your answer. Pause whenever you need a longer think. Have fun with it. Keep your focus here. Question 1. Spot the narrowing word. A generative AI engineer at Conteso Finance is registering a fraud detection model to the production model registry in Unity Catalog using MLflow. The production catalog is named ops_prod. The schema for machine learning models is security_ML, and the model should be registered as fraud_classifier. What is the correct value to pass to the name parameter of elflow.register_model? Select 1. Review the answer choices on screen. The correct answer is option D. The dot delimiter is Unity Catalog's only valid separator. Unity Catalog uses a 3-level dot delimited namespace for every managed object, including registered models. The required format is catalog.schema.model_name, so ops_prod.security_ml.fraud_classifier is the correct argument to pass as the name parameter. Providing only the model name fraud_classifier without catalog and schema qualifiers either resolves to the legacy workspace level registry or fails outright when elflow is configured with the Databricks UC registry URI, which is the default in elflow 3. // are not valid namespace separators in Unity Catalog syntax and will cause the registration call to fail with an error. Colons are equally invalid as namespace delimiters for Unity Catalog objects and will produce the same registration failure. Keep your focus here. Question 2. Test each option against the full ask. A generative AI engineer at Dunmore Financial is exposing an internal LLM assistant to 500 employees via a model serving endpoint fronted by AI Gateway. Leadership is concerned that unrestricted usage during peak hours could cause monthly costs to exceed budget and could degrade response quality for business-critical workflows. Which AI Gateway capability should the engineer configure to address both concerns? Select 1. Review the answer choices on screen. The correct answer is option C. PII detection and safety filters act on content, not volume. Rate limiting in AI Gateway allows the engineer to set query per minute or token per minute ceilings scope to the endpoint as a whole, to individual users, or to defined groups. This directly prevents cost runaway by capping total token consumption and protects service quality for business-critical users by preventing any single user or burst of activity from exhausting endpoint capacity during peak hours. PII detection inspects and redacts personal data from individual requests, but has no mechanism to constrain overall throughput or enforce spending limits. Safety filtering rejects requests with harmful content categories, but is not designed to manage usage volume, control aggregate costs, or differentiate service priority between workflow types. Traffic tracking provides post-hoc visibility into usage patterns for reporting purposes, but does not actively restrict traffic or cap costs in real time during the period when the overrun is actually occurring. Okay, careful on question 3. This one has a trap. A generative AI engineer at Clearwater Analytics is creating a provisioned throughput foundation model API endpoint to serve an LLM for large document summarization under sustained high concurrency load. Which two parameters are required when configuring the provisioned throughput endpoint to reserve capacity and define a scaling ceiling? Select 2. Review the answer choices on screen. The correct answers are option B and option D. Two bounds define the reserved capacity range: floor and ceiling. Provisioned throughput endpoints require min_provisioned_throughput and max_provisioned_throughput to be specified at creation time. Min_provisioned_throughput sets the guaranteed floor of tokens per second that the endpoint always maintains, ensuring consistent low latency even under sustained load. Max_provisioned_throughput defines the scaling ceiling, capping how far the endpoint will scale up. Together, these two parameters bound the reserved capacity range. Sampling_fraction is an inference table configuration parameter that controls what proportion of requests are captured for logging and is unrelated to throughput reservation. Concurrent_request_limit is not a provisioned throughput configuration parameter. Pay_per_token_fallback does not exist as a provisioned throughput parameter. Pay per token and provisioned throughput are distinct endpoint types that cannot be combined. Okay. Question 4. Read the ask, not just the topic. A generative AI engineer at Parkview Technology is building a legal document discovery system using hybrid keyword and vector search over a large case law corpus. During testing, they noticed that queries return a maximum of 200 results, even though thousands of potentially relevant documents exist in the index. What is the cause of this limit? Select 1. Review the answer choices on screen. The correct answer is option A. Hybrid and full text cap at 200. ANN supports up to 10,000. Hybrid search and full text search modes in Databricks AI Search have a platform-defined ceiling of 200 results per query. This limit is specific to these search modes and is by design. In contrast, approximate nearest neighbor queries support up to 10,000 results. The HNSW algorithm does not impose a 200 result output cap. Its performance characteristics are governed by index construction parameters such as f_construction, not a hard result count limit. The RRF_param is a constant in the reciprocal rank fusion formula that controls the balance between keyword and vector ranking contributions during score fusion. It does not define a result count ceiling. ANN query limits are unaffected by whether embeddings have been cosine normalized. Normalization affects how distances are interpreted, not how many results are returned. Okay. Question 5. Let the constraints drive the choice. A generative AI engineer at Ironwood Research is building a RAG system over a large corpus of academic papers. Evaluation revealed two competing problems. Small chunk sizes produce highly precise retrieval results, but give the LLM too little surrounding context to generate complete answers, while large chunk sizes provide richer context but reduce retrieval precision. The engineer wants a single architecture that achieves precise retrieval and rich generation context simultaneously. Which chunking approach should they adopt? Select 1. Review the answer choices on screen. The correct answer is option C. Decoupling retrieval granularity from generation context is the key move. Parent-child retrieval directly addresses the dual requirement by decoupling retrieval granularity from generation context length. Small 512 token child chunks are indexed and used during the retrieval step, giving the search stage high precision by matching queries against focused, specific passages. When a child chunk is selected, the system looks up its larger 2048 token parent segment and passes that richer context to the LLM for response generation. This independently optimizes each phase without forcing a compromise. Semantic chunking improves boundary quality by grouping topically related sentences, but every chunk is still used for both retrieval and generation at the same granularity. It does not provide a mechanism for serving different sizes to each stage. Fixed-size chunks with overlap soften boundary effects but still commit to a single chunk size for both search and context, recreating the original trade-off rather than eliminating it. Recursive character splitting at 200 tokens produces short, precise chunks suitable for retrieval, but provides no path to expanding context at generation time after a passage is found. Unity Catalog forces catalog.schema.model, dots only, no slashes. Rate limiting is AI Gateway's real-time spending break, and parent-child retrieval, small chunks to search, large parent for context, has already appeared twice. Here we go. Question 6. Do not answer a different question. A generative AI engineer at Fabricam Legal is evaluating an AI search hybrid index for a contract search system. Documents containing a legal keyword many times rank disproportionately higher than focused, shorter contracts that use the term precisely once or twice. The engineer wants to reduce the influence of repeated keyword occurrences on scoring without changing how the system normalizes document length. Which BM25 parameter adjustment should the engineer make? Select one. Review the answer choices on screen. The correct answer is option B. The phrase "without changing length normalization" eliminates the B parameter. The K1 parameter in BM25 controls term frequency saturation, the rate at which additional occurrences of a term stop, meaningfully increasing a document's score. Lowering K1 causes saturation to kick in sooner, so the 50th occurrence of a keyword contributes far less marginal gain than it would at a higher K1 value. This directly resolves the problem of keyword-dense documents drowning out more focused answers. The B parameter governs document length normalization rather than term frequency behavior. Increasing B would penalize longer documents broadly, but would not specifically dampen the influence of keyword repetition, and the engineer explicitly wants to leave length normalization unchanged. Decreasing B reduces length normalization entirely, which would amplify the existing advantage that long, keyword-heavy documents already enjoy. Increasing K1 raises the saturation ceiling, making each additional keyword occurrence more influential, which is the opposite of what the engineer needs. 2 BM25 parameters, two very different jobs. Let's put them side by side and clear this up. Picture a 200-page contract that repeats indemnification 80 times. It outranks a tight 2-page addendum that uses the term twice. BM25 has two knobs. K1 is a saturation dial. It controls how much the 50th keyword hit still boosts the score. Lower K1 means you hit the ceiling fast, so repetition stops helping. The B parameter is a length dial. It penalizes long documents broadly. The engineer wants to tame repetition but leave length scoring alone. That's K1's job, not B's. Touching B answers the wrong question. Decrease K1. The exam rewards knowing which knob does which job. Next up, question 7. Keep the constraints in view. A generative AI engineer is building a RAG system for a legal contract analysis platform. During evaluation, she observes that short, focused chunks produce highly precise retrieval matches, but the LLM often lacks sufficient surrounding context to generate complete answers. Longer chunks preserve context, but reduce retrieval precision by grouping unrelated clauses into a single embedding. Which indexing and retrieval strategy resolves both constraints simultaneously? Select one. Review the answer choices on screen. The correct answer is option D. Same architecture. Small chunk search, large parent segments feed the LLM. Parent-child retrieval decouples retrieval granularity from context provision. Small 512-token child chunks are embedded and indexed, so each embedding represents a narrow, focused concept that maximizes retrieval precision. When a child chunk is matched, the system returns the larger 2048-token parent segment that contains it, giving the LLM full surrounding context for answer generation. This directly resolves both observed problems without sacrificing either precision or completeness. Simply increasing chunk size to 2048 tokens improves context, but degrades retrieval precision as the original diagnosis states. Semantic chunking produces semantically coherent segments, but does not separate the granularity used for retrieval from the granularity used for context provision. So the precision versus context tension remains. Fine-tuning. The embedding model is resource-intensive and only partially improves retrieval quality on long chunks, without addressing the fundamental mismatch between what is useful for retrieval and what is useful for generation. Next up, question 8. Follow the operational constraint. A generative AI engineer at Fabricam Finance is expanding an existing LangChain RAG assistant to answer questions about product sales performance. The new data source consists of structured quarterly revenue and unit sales figures stored in Delta tables. The engineer needs to integrate this structured source alongside the existing unstructured document corpus. Which approach is most appropriate for retrieving data from the structured Delta tables? Select one. Review the answer choices on screen. The correct answer is option A. Embedding table rows cannot aggregate or return exact numeric results. Structured data stored in relational tables is best queried through SQL, not through vector similarity. A SQL-based retriever generates a structured query tailored to the user's question and executes it against the Delta tables, returning precise numerical results such as specific revenue figures, unit counts, and regional breakdowns that semantic search cannot reliably produce from numerical data. Embedding each table row and indexing it in AI search applies unstructured text retrieval to inherently structured data, which does not leverage the query precision that SQL provides and yields unreliable results for exact numerical lookups and aggregations. Serializing rows to JSON strings and adding them to the vector store has the same fundamental problem. Semantic similarity is not the right retrieval mechanism for structured numerical queries where exactness and aggregation matter. Exporting tables as PDFs and running them through the document pipeline converts structured data into an unstructured format, destroying the schema and making precise numerical queries impossible. Next up, we're on question 9. A generative AI engineer at Pinewood Digital is deploying a shared foundation model API endpoint used by 8 product teams simultaneously. During peak hours, a single high-volume team sends thousands of requests per minute, causing degraded response times for all other teams and threatening contractual SLA commitments. The platform team needs a native way to enforce per-team consumption limits without modifying any application code. Which AI gateway feature should they configure? Select one. Review the answer choices on screen. The correct answer is option D. Per-group QPM caps enforce fairness without touching any client code. Rate limiting in AI Gateway allows the platform team to enforce per-user or per-group query per minute and token per minute caps directly at the endpoint layer, preventing any single team from monopolizing shared capacity without requiring changes to client applications. Safety filters analyze content for harmful material and have no mechanism to throttle legitimate high-volume requests from a specific team. PII detection inspects content for personal identifiers and takes action based on data sensitivity, not request volume or team identity. Traffic splitting distributes load across back-end model endpoints and can improve availability, but it does not constrain how many requests any given team or user is permitted to send. Now, question 10. Prioritize the stated requirement. A generative AI engineer at Bridgepoint Research is building a RAG system over an archive of academic survey papers. Each paper covers multiple distinct subtopics that shift gradually throughout the document. The team's top priority is that each retrieved chunk represents a single coherent topic rather than straddling two different discussions, and they are willing to accept slower offline pre-processing. Which chunking strategy best fits these requirements? Select one. Review the answer choices on screen. The correct answer is option A. Embedding similarity detects topic shifts that paragraph rules never see. Semantic chunking uses an embedding model to measure the similarity between adjacent text segments and places chunk boundaries where topic similarity drops sharply, exactly at the points where a survey paper transitions from one subtopic to another. The result is chunks where each segment discusses a single coherent theme, at the cost of more expensive pre-processing compute relative to rule-based approaches. Fixed-size chunking ignores all content boundaries and frequently bisects a single topic across two adjacent chunks, directly violating the coherence requirement. Recursive character splitting respects syntactic structures such as paragraphs and sentences, but relies on rule-based heuristics rather than embedding similarity, so it cannot detect when a new paragraph begins a semantically distinct subtopic. Parent-child retrieval is a retrieval time strategy for balancing search precision against context window size, and does not define topic coherent boundaries at indexing time. BM25K1 governs term frequency saturation, not B, to dampen keyword spamming. Structured delta data demands SQL retrieval, never embeddings. Semantic chunking detects topic boundaries that paragraph rules miss. Now, let's open question 11. A data science team is migrating their model management workflow to Databricks with MLflow 3. A junior engineer is surprised to find that newly logged models are automatically appearing in Unity Catalog, rather than the workspace model registry they used previously. What explains this behavior? Select one. Review the answer choices on screen. The correct answer is option C. MLflow 3 changed the default registry silently, a migration surprise. In MLflow 3, the default registry URI is Databricks UC, which directs all model registration to Unity Catalog rather than the classic workspace model registry. This is a deliberate platform change that centralizes model governance under Unity Catalog by default, giving teams access to Unity Catalog lineage, access controls, and the three-level catalog schema model namespace from the moment they register a model without additional configuration. MLflow does not detect Unity Catalog through runtime cluster inspection to switch registries dynamically. A global administrator policy is not the mechanism driving this behavior. It is a built-in default in MLflow 3 itself. Change data feed is a delta table feature for streaming incremental changes to downstream consumers, and has no connection to where MLflow registers model versions. Let us keep moving. Question 12. Every phrase counts. A generative AI engineer is designing an evaluation framework for a legal research assistant. The knowledge base contains documents with varying relevance levels, highly authoritative primary citations, useful background material, and many irrelevant documents. The team wants a single retrieval metric that penalizes placing a highly authoritative document at rank 5 more than at rank 2, and also distinguishes between partial and zero relevance. Which metric best satisfies both requirements? Select one. Review the answer choices on screen. The correct answer is option A. Two simultaneous requirements, graded relevance and rank position discounting. NDCG, normalized discounted cumulative gain, satisfies both requirements simultaneously. It supports graded relevance scores, distinguishing between highly authoritative, partially relevant, and irrelevant documents rather than collapsing judgments into a binary decision. It also applies a logarithmic position discount, so a highly relevant document ranked at position 5 contributes less to the final score than the same document at position 2. NDCG then normalizes against the ideal ranking, producing a value between 0 and 1 where 1.0 represents perfect ordering. Recall at K measures completeness of retrieval but uses binary relevance and entirely ignores ranking position. Precision at K also treats relevance as binary and measures density at a cutoff without penalizing poor positioning of high-value documents. F1 at K averages precision and recall but still relies on binary relevance judgments and provides no position-weighted scoring. Let's slow down here. The NDCG metric is worth really seeing in numbers. Imagine your legal assistant finds the perfect case citation but it lands at rank 5 instead of rank 1. Does that hurt your score? With NDCG, yes, and here's exactly how much. A document at rank 1 carries full weight, 100%. Move it to rank 2 and it drops to 63%. Rank 3 cuts it to 50%. By rank 5, you're down to just 39%. That's the position weighting piece. NDCG also handles graded relevance. Primary citations, background reading, and irrelevant noise each get different scores. The other options use binary relevance, in or out. They can't separate a landmark case from a tangential article. The exam asks for both position weighting and graded relevance. Only NDCG delivers both. That's the answer. Time for another one. Question 13. Close is not correct. A generative AI engineer is designing a feature-serving endpoint for a real-time pricing recommendation system. The endpoint must retrieve a customer's historical purchase count and average order value from a pre-materialized feature table. It must also compute a discount eligibility flag on demand by applying a Python business rule to those retrieved values. Which two feature spec components does the engineer need to configure this endpoint? Select 2. Review the answer choices on screen. The correct answers are option A and option C. 3 of the 5 options describe components that do not exist. Feature lookup retrieves specific columns from a pre-materialized online feature table by matching a lookup key such as customer ID, which is precisely what is needed to pull historical purchase count and average order value at serving time. Feature function applies a user-defined Python function as an on-demand transformation, handling the discount eligibility computation that depends on the just retrieved values and must reflect current business logic. Together, these two components cover the full requirement, pre-materialized retrieval plus on-demand computation within a single feature spec. Feature vector is not a component in the Databricks Feature Serving API. Features flow as standard columns rather than a serialized dense object. Feature pipeline is not part of the Feature Serving API. The feature spec definition implicitly orchestrates the order of lookups and functions without a separate pipeline construct. Feature cache is not an available feature spec component. Feature serving endpoints manage serving latency through their own dedicated compute infrastructure without an explicit caching layer that engineers configure. 3 of these 5 options don't exist at all. Let's figure out which 2 actually do. Imagine you're building a pricing bot for an e-commerce site. It needs 2 things at request time. First, a customer's 90-day purchase history, already stored in a table. Second, a fresh discount flag, computed right now from those stored values. Those are 2 different jobs. If a value sits in a feature table, you fetch it by key. That's feature lookup. If you need Python logic applied at the moment of the request, that's feature function. Feature vector, feature pipeline, and feature cache all sound official, but none of them exist in the API. The exam makes up plausible-sounding names. That's the trap. Time for another one. Question 14. Convert the story into selection criteria. A generative AI engineer is selecting a chunking strategy for a RAG system built on a large corpus of academic research papers. Some papers use formal section headers while others are written as continuous prose with no structural markers. The primary requirement is retrieval coherence, Each retrieved chunk should represent a complete, self-contained idea rather than an arbitrary slice of text. Computational cost is a secondary concern. Which chunking strategy best satisfies this requirement? Select one. Review the answer choices on screen. The correct answer is option B. Papers without headers disqualify context-aware chunking immediately. Semantic chunking groups adjacent sentences based on their embedding similarity, so each chunk naturally contains text unified around a single topic. Because it operates on semantic content rather than structural markers or fixed token counts, it works consistently across both formally structured papers and free-form prose. This directly addresses the retrieval coherence requirement. Fixed-size chunking enforces a token limit mechanically without regard to topic or sentence boundaries, frequently bisecting related ideas across chunk edges. Recursive character splitting uses structural separators like paragraph breaks, which improves over pure fixed-size splitting, but still depends on character patterns rather than semantic content, producing less topically coherent chunks when prose lacks clear separators. Context-aware chunking relies on document structural metadata and section headers, which the problem states are absent from a substantial portion of the corpus, making it unreliable for the full collection. Time for another one. Let's check question 15. A generative AI engineer at Redfield Labs is debugging a RAG pipeline that produces incomplete answers on complex questions. Inspection of retrieved chunks reveals that many critical concepts are split across chunk boundaries. A key clause ends abruptly at the close of one chunk, and its continuation only appears at the start of the next. What configuration change most directly resolves this issue? Select one. Review the answer choices on screen. The correct answer is option D. Overlap is the simplest, cheapest fix for boundary context loss. Adding a 10 to 20% token overlap between consecutive chunks is the standard technique for preventing loss of context at chunk boundaries. When a chunk begins at exactly the point where the previous chunk ended, concepts that straddle the boundary are split with no redundancy. Overlap ensures the tail of each chunk is repeated at the head of the next, so the LLM receives sufficient surrounding context to interpret boundary-crossing sentences. Bypassing chunking entirely by storing full documents would quickly exceed most embedding model context lengths and force the LLM to process far more text than necessary per retrieval call. Filtering out short chunks addresses a different problem and removes legitimate small chunks without fixing boundary truncation. Reducing the embedding model's context window worsens the problem by forcing even more aggressive truncation rather than producing tighter semantic alignment. MLflow 3 defaulted to Databricks UC, catching migrators off guard. NDCG handles graded relevance and rank position penalty in one metric. Chunk overlap is the cheapest fix when concepts bleed across boundaries. Ready. Question 16. One detail changes the answer. A generative AI engineer is implementing an LLM as judge pipeline using MLflow scorers to evaluate how relevant each retrieved chunk is to the user query in a RAG system. What is the standard relevance scale that the judge applies when scoring each chunk? Select one. Review the answer choices on screen. The correct answer is option A. Databricks MLflow uses exactly 4 levels, 0, 1, 2, 3. The standard relevance scale used by LLM as judge scorers in Databricks MLflow evaluation is a 4-point scale from 0 to 3. A score of 0 means the chunk is not relevant to the query, 1 means it is partially relevant, 2 means it is relevant, and 3 means it is highly relevant. This graded scale allows the judge to distinguish between degrees of relevance rather than producing a binary result, making it more informative for diagnosing retrieval quality and tracking improvement over time. MLflow also tracks Cohen's kappa and F1 scores against human judgments using this same scale. Scales of 0 to 5, 1 to 4, and 0 to 10 are not the standard defined for this evaluation framework and would produce results incompatible with the built-in MLflow scorers. This one's about a specific number. Let's nail exactly what scale the judge uses. Imagine grading a friend's movie recommendations. You'd say totally off, a bit related, pretty good, or perfect. MLflow's chunk relevance judge works the same way. It scores each retrieved chunk from 0 to 3. 0 means the chunk has nothing to do with the query. 1 is partial, 2 is relevant, 3 means it directly answers the question. Say your RAG pipeline pulls 10 chunks. The judge grades every one. Precision is the share that scored a 2 or higher. The trap answers give you other scales: 0 to 5, 1 to 4, or 0 to 10. None of those match the built-in scorer. On the exam, remember, it's 0 to 3, 4 levels, starting at 0. Let us switch gears. Question 17. Follow the operational constraint. A generative AI engineer at Northfield Tech is launching a new internal knowledge assistant backed by foundation model APIs. The tool enters a 2-week pilot with a small group of employees and daily request volume is unpredictable. Usage may be near 0 on some days. The team wants to minimize costs during the pilot while retaining a straightforward path to a production-grade deployment afterward. Which serving configuration is most appropriate for the pilot phase? Select one. Review the answer choices on screen. The correct answer is option C. Provisioned throughput charges persist even at 0 traffic. Pay-per-token foundation model API endpoints are the Databricks recommended starting point for new applications where traffic is uncertain. Because costs scale directly with token consumption rather than a fixed reservation, the team incurs no cost during periods of 0 usage and scales seamlessly as pilot adoption grows. Provisioned throughput endpoints allocate dedicated compute capacity measured in model units and require a minimum throughput reservation to maintain a warm, ready state. They are not designed for near-zero traffic scenarios and carry a fixed cost regardless of actual usage levels. External model endpoints through AI Gateway introduce dependency on third-party providers with separate billing and capacity agreements, adding unnecessary complexity for a 2-week internal pilot. Custom model endpoints on single-node clusters with scale-to-zero configuration introduce cold start delays on resumption and require ongoing cluster management, which is operationally heavier than warranted for a limited discovery phase. Keep your focus here. Question 18. Check the condition before the service. A generative AI engineer is configuring a provisioned throughput endpoint on Databricks for a high-volume production text generation service. The team requires guaranteed minimum capacity with the ability to scale up automatically under peak load. Which 2 parameters must they specify when configuring the provisioned throughput endpoint? Select 2. Review the answer choices on screen. The correct answers are option B and option D. RRF_param and embedding_dimension come from different subsystems entirely. Provisioned throughput endpoints require both min_provisioned_throughput and max_provisioned_throughput to define the scaling bounds. The minimum value guarantees a floor of reserved capacity so the service maintains consistent latency even when traffic is low, while the maximum value caps how far auto-scaling can extend to control costs. Sampling_fraction is a parameter used by inference tables to set what fraction of requests are captured for logging, and has no role in throughput configuration. RRF_param is the reciprocal rank fusion parameter used in hybrid AI search queries to blend keyword and semantic ranking scores. Embedding_dimension is a property of the embedding model or index configuration, not a serving endpoint throughput parameter. Keep your focus here. Question 19. The scenario tells you the trade-off. A generative AI engineer at Northgate AI is iterating on the system prompt for a customer service assistant. 2 candidate prompt templates have been developed, and both receive similarly high scores when evaluated independently by an LLM judge. Standard independent scoring has failed to clearly differentiate the 2 templates. Which evaluation methodology should the engineer use to more reliably identify which template produces better responses? Select one. Review the answer choices on screen. The correct answer is option B. Head-to-head comparison surfaces relative quality that independent scores compress. Pairwise comparison is purpose-built for directly contrasting 2 candidate outputs. By presenting the query and both responses to the judge simultaneously and asking it to select the better one, this methodology captures relative quality differences and produces judgments that align more closely with human preference than independent scoring does. Single output scoring evaluates each response in isolation, which introduces inter-run variance and score compression near the top of the scale. When 2 templates produce similarly strong responses, aggregate averages often fail to discriminate between them reliably. Eval with chain of thought is a single output technique in which the judge reasons step by step before assigning a score to one response. It is not designed for head-to-head comparison of 2 candidates and shares the same instability drawbacks as other pointwise scoring methods. Retrieval groundedness measures whether a response is supported by retrieved context and is a RAG faithfulness metric, not a mechanism for comparing prompt template quality. All right. Question 20. Identify the business need first. A generative AI engineer at Wingtip Media is building a video metadata search system that must index over 2 billion embedding vectors at 512 dimensions. The team requires indexing throughput that is 10 to 20 times faster than the standard tier and can accept up to 300 milliseconds of additional query latency. Which Databricks AI search endpoint type should the engineer select? Select one. Review the answer choices on screen. The correct answer is option A. 2 billion vectors and 10 times faster indexing, only one option fits. Storage-optimized endpoints are designed for vector corpora exceeding 1 billion vectors and deliver 10 to 20 times faster indexing throughput compared to standard endpoints, making them the appropriate choice for a 2 billion vector corpus with high indexing demands. The trade-off is approximately 250 milliseconds of additional query latency, which falls within the team's stated tolerance of 300 milliseconds. Standard endpoints are designed for corpora of approximately 320 million vectors at 768 dimensions and would be severely under-provisioned for a 2 billion vector corpus. Manual shard scaling is not an independently configurable option for standard endpoints in Databricks AI Search. Pay-per-token foundation model API endpoints serve language model inference requests and are entirely unrelated to AI search indexing or vector retrieval. Let's slow down on this one. The question hides 4 number-shaped clues that each kill a wrong answer. Imagine you're building a Netflix-style metadata search for every video ever uploaded. 2 billion clips. That's not a standard job. That's a warehouse job. The question loads the stem with precise numbers that each eliminate a wrong answer. 2 billion vectors blows past the standard endpoint's 320 million ceiling. The 10 to 20 times faster line is practically quoted from the storage-optimized spec sheet, and 300 milliseconds of latency tolerance? That's the question giving you permission to pick the endpoint that adds around 250 milliseconds. The trap is overthinking the latency clause, treating it as a red flag rather than a green light. 3 takeaways from this session. First, Parent-child retrieval decouples search granularity from context size, satisfying precision and completeness together. Second, NDCG is the only retrieval metric that simultaneously handles graded relevance and rank position discounting. Third, 3 of the 5 feature spec options are platform inventions, only feature lookup and feature function exist. Parent-child chunking, BM25 tuning, NDCG scoring, and endpoint sizing are 4 distinct leverage points. Nail them independently and the whole system lifts.